I'd like to talk today about some incredibly useful recent results in the field of data-driven modeling. This work, which is the primary topic of Patrick Reinbold's dissertation, is a modification of symbolic regression that allows us to derive minimal partial differential equation models for experimental fluid flow data, even under some of the worst possible conditions under which the leading algorithms currently fail. Namely, we'll look at data that is corrupted by noise and has missing observables. We'll begin with an introduction to our experimental setup and a description of the type of model that we're attempting to discover. Then we'll discuss the process of creating a candidate model from geometric and physical constraints and insights. Next, we'll introduce a weak formulation of the symbolic regression algorithm, which allows us to perform symbolic regression on noisy experimental data with latent variables. We'll look at our results and compare them to previous studies that have attempted first principles approaches for model acquisition. Last, we'll demonstrate the reconstruction of those latent variables by using the parsimonious model retrieved from symbolic regression. The experimental setup seen here is designed to mimic Kolmogorov flow, a two-dimensional flow that's sinusoidally forced. To replicate that, we place a shallow layer of electrolyte in a rectangular box which has electrodes on either end for driving a current in the y direction. Underneath the box is an array of permanent magnets with alternating polarity, which generates a magnetic field in the plus or minus z direction. This results in a Lorentz forcing profile in X that varies approximately sinusoidally in Y in the center of the domain. In order to overcome the no-slip boundary condition imposed by the bottom of the box, the electrolyte floats on top of a shallow layer of denser, immiscible dielectric. The resulting velocity profile, as a function of z, is nearly vertical within the electrolyte. The free surface and liquid-liquid interface move with nearly the same velocity, making this flow quasi-two-dimensional. The interface is seeded with tracer particles, and a camera mounted above the setup takes videos. The velocity field is then reconstructed using particle image velocimetry. A typical velocity field X component is shown on the right at a Reynolds number of about 20. The full three-dimensional flow should be described well by the standard Navier-Stokes equation. However, we don't have knowledge of the full 3D flow since we only image from one direction. Therefore, we want a 2D candidate model for the flow that accurately describes an inherently three-dimensional system. In order to build our candidate 2D model, we first identify the relevant fields. For this flow, these are the horizontal velocity, the pressure, and the forcing profile, which is time independent. We then write a sum of terms in these fields that respect the Euclidean symmetries of the system. We can add as many terms as we like, but here we remove the higher derivatives and terms of higher order in the velocity, forcing, and pressure gradient. We also assume that this flow is incompressible, which greatly limits the types of terms that can be used. Here's a brief demonstration of sequentially thresholded symbolic regression for this particular system. We start with a snapshot of the flow at one point in time and our candidate model. Looking at one point in space, we write numerical values for each of the terms in the model. This is done for many randomly sampled points in the domain. These numerical values are then loaded into the vector Q0 and library matrix Q hat. Iterative linear regression then removes terms that are small compared to a threshold, until you're left with a parsimonious model with coefficients c. This approach works well for numerical, low-dimensional data, but for fluid experiments that are noisy and have missing information about pressure, for instance, this method is not feasible. Noise corrupts the data, which is exacerbated even further with every derivative that's taken. Since SINDI and other approaches to constructing PDE models directly from the data only work when we have reliable information about the derivatives and all the fields to satisfy the linear system with a full rank Q matrix, we will instead need to use a weak formulation of symbolic regression, which is much more capable of handling this level of noise. To overcome the issues associated with experimental noise, we sample not just points in time, but large areas of the flow domain. Over each sample area, omega I, we multiply each term in the candidate model by a weight function and integrate. The choice of weight function here is not arbitrary. Specifically, we choose it to eliminate terms with latent variables and to move derivatives off of the noisy data. However, there will still be a lot of freedom in choosing the weight function, since many different weight functions may achieve these same goals. Once these integrals are evaluated, we use the results to fill in the entries of our Q matrix and perform symbolic regression. Here we sample a central region covering about 80% of the total domain, so we don't sample the boundaries, which are associated with larger PIV noise due to the small fluid velocity. With the origin of the system at the center, it makes sense to give this region a width of 2hx and a height 2hy. We then select random samples in time with length 2ht. This gives a simple inequality definition for our domains omega I. Our first goal in choosing the weight function is removing the pressure and forcing terms, which from experimental data are unavailable. When we integrate the forcing, we integrate over space and time. but the forcing is time independent. This means that any weight function that's odd in time will remove the forcing term. We can perform integration by parts on the pressure integral, and assuming the boundary terms vanish due to physical restrictions on the pressure, we find that the weight function must be divergence-free to eliminate the pressure term. This means another constraint on our weight function is that it can be the curl of some function psi in the z direction. Here we perform the remaining integrations by parts, where possible. To remove the boundary terms for the time derivative integral, the weight function must vanish on the boundary. For the first advection term, we need the derivatives to vanish on the boundary, and for the diffusion term, we need the second derivatives to vanish on the boundary. Looking at our model, we've managed to remove the latent variables, as well as terms with derivatives of noisy data in all terms but one. While this term can be manipulated a little, the end result still requires at least one derivative of u, so we leave it unchanged and use either Fourier or Tikhonov methods for taking the derivatives here, which are far less noisy than simple difference derivatives. Gathering our restrictions, we're able to concoct a few candidates for the weight function. Rescaling the variables so that they vary from -1 to 1, we can write psi as a product of Legendre polynomials p and envelope functions e in all three dimensions. The envelope function satisfies the boundary conditions so long as alpha and beta are greater than or equal to 3, and we typically match gamma to these parameters as well. For the weight function to be odd in time, we constrain nu to be 1, but lambda and mu can take either 0 or 1. These parameters provide a lot of flexibility in choosing the weight function. In fact, one can choose multiple weight functions and stack the results of those integrals to create larger Q matrices. We now run symbolic regression, removing one term at a time using a thresholding criteria. We select some epsilon, and if a term is smaller than epsilon times Q naught, we discard that term and run the regression again until no small terms remain. Performing this procedure with many different values of epsilon results in this plot, where PID is the proportion of trials in which a particular term is identified. We want to select epsilon in a range where the same terms are consistently removed and the identified model fits the data well as indicated by a low residual. We see that at a very low epsilon, no terms are removed, so the model is overfitting. Up to 0.1, terms are removed. Between 0.1 and 0.3, no new terms are removed, and finally above 0.3, the final terms are removed. The system is then underfitting and no longer accurately describes the flow. Therefore, we select epsilon to be in the range 0.1 to 0.3. This threshold allows symbolic regression to consistently return a parsimonious model that describes the data well, which consists of the first three terms. Shown here is the residual for an epsilon of 0.1. Across the range of Reynolds numbers tested, the residual is fairly low, with the only exceptions being at very low Reynolds number. We expect that this is because at Reynolds numbers lower than 20, the flow first becomes time periodic, then nearly stationary. Since our weight function removes terms that are time independent, approaching stationary flow will give spurious results since the Q matrix is no longer full rank. Here is our parsimonious model, just advection, diffusion, and a linear Rayleigh friction term, plus pressure and forcing. An indication that this model makes sense is that it agrees with the first principles approach derived by Suri and others in 2014. They posit that we can separate the full 3D flow into a horizontal flow multiplied by a vertical velocity profile. By plugging this ansatz into the Navier-Stokes equation and solving the resulting differential equation, they recover the velocity profile as a function of the fluid parameters. They then average the Navier-Stokes equation through the depth of the fluid and generate this two-dimensional model for the flow. These are coefficients that they compute with their choice of fluid parameters. The assumption that the 3D velocity can be decomposed falls apart at even moderate Reynolds number when the flow no longer mimics the forcing profile. However, their model is exactly the same as the one we've recovered using symbolic regression, but with slightly different coefficients even at the same fluid parameters. These three plots show the coefficients retrieved from symbolic regression in black and the coefficients from Suri's model in red. All of these parameters are the same order of magnitude, but do vary slightly from the derived values, indicating some missing physics in their original assumptions. Another interesting point to note is that these values are stable over this range of Reynolds number, with the exception of C2 at the low end of the range, in which the data starts becoming time independent. Yet another point of validation for our candidate model is that we can reconstruct the latent variables for our system. First, we collect the known parts of the model and set them equal to a function S. This function is also equal to the sum of the unknown latent parts. Next, we perform a Helmholtz decomposition on S, take a Fourier transform of that decomposition, and solve for the pressure and forcing by inverse Fourier transform of phi and A. Note here that we've used the fact that S points only in x and y to simplify calculations. We take the time average of the forcing integral, both to smooth the forcing field and to ensure that it's time independent. In rotational vortices, pressure is lowest and vorticity is the highest at the center of each vortex, So to provide a qualitative look at the resulting pressure field, we examine negative pressure on the left and the absolute value of vorticity on the right. As the flow field evolves, we can make a qualitative comparison between the yellow maxima of these two functions, which are quite similar by eye. To test the validity of the reconstructed forcing profile, we measured the magnetic field on a fine grid. Since the forcing strength is proportional to the magnetic field strength, we can qualitatively compare the shape of these two profiles for an idea of the performance of the Helmholtz decomposition. From these heat maps, we see that in the middle of the domain, the forcing is reconstructed fairly reliably. It's only around the boundary, which is not within the symbolic regression's integration domains, that the performance is not as strong. For an even more telling plot, we can look at comparison along the white dashed line here. Along the 1D slice at the center line x equals 0, we can see the excellent agreement between the shapes of the reconstruction and the measured field. These fields have both been scaled by their maxima here to allow us to plot them on the same axes. So in summary, we've shown that we can use physical intuition and symmetry arguments to create candidate PDE models for complex systems. Using a weak formulation of symbolic regression, we're able to remove unnecessary terms from this model one at a time until we're left with a parsimonious governing equation. This is possible even with missing variables and in the presence of experimental noise. After the model is fully identified, we can recover the latent variables using a Helmholtz decomposition in the case of our quasi-2D Navier-Stokes model. This method is proving very robust, and we look forward to pushing it to its limits with even more complicated and higher dimensional systems. Thank you so much for your attention during this virtual presentation. I'll be available to take questions during session K9, which is 8:45 to 9:30 a.m. in Chicago time on Monday. Enjoy the rest of the conference and stay safe.